Hello everyone, welcome to Chapter 7, we will deal with OSPF in this chapter. Our first topic is OSPF concept, our next topic is to make OSPF applications, and finally we will finish this topic by talking about OSPF network types and neighborhoods. In this lesson, we will first talk about the basics of OSPF, then we will examine the interior and exterior routing protocols, then I will talk about administrative distance, and finally we will complete our lesson by talking about OSPF neighborhood building and OSPF LSA packages. First, let me tell you the basics of OSPF. OSPF, it is an open standard routing protocol used by many manufacturers, including Cisco. If you have more than one router and they are not all Cisco, you cannot use EIGRP. Your remaining options are basically RIP, RIPv2 and OSPF. If you have a large network, then our only option is to use OSPF and also to do route redistribution between other routing protocols. If you use both OSPF and EIGRP on the router, you redistribute the routes you learn from EIGRP to OSPF, in the same way that you redistribute the routes you learn from OSPF to EIGRP and send them to the EIGRP routing protocol. OSPF works using the Dijkstra algorithm. A shortest path tree is configured first, and the resulting best routes are placed in the routing table. Both support equal cost routes, even if they are not as fast as EIGRP, and like EIGRP, OSPF supports both IPv4 and IPv6 routed protocols. Let's talk about some of the advantages that OSPF gives us. It consists of areas and autonomous systems, minimizes routing update traffic, provides scalability, supports subnets and prefixes, has unlimited hop counts, and is a link state routing protocol supported by many manufacturers. Now let's talk about the routing protocol. Routing protocol, it consists of a set of messages, rules, and algorithms used by routers to learn routes. This process involves exchanging and analyzing routing information, with each router choosing the best route for each subnet and finally placing these routes in the IP routing table. Examples of routing protocols include RIP, EIGRP, OSPF, and BGP. There are also routed and routable protocols, and we can give IPv4 and IPv6 as examples. Routing protocols are divided into two as interior and exterior. Interior gateway protocol. It is a routing protocol designed for use within a single autonomous system, examples of which we can give are IPv2, EIGRP and OSPF. The exterior gateway protocol is a routing protocol designed to be used between different autonomous systems, and BGP is an example. The figure here shows an example for IGP and EGP. The corporate network here also used the EIGRP routing protocol in a single autonomous system. OSPF was used in the company here. ISP2 and ISP4 used EIGRP in their internal networks. ISP3 used OSPF, but ISP2 uses BGP, which is the external gateway protocol when it will establish a connection with ISP3. In the same way it needs to use BGP to establish a connection with ISP4. When the ISP3 in the figure is going to connect with a corporate customer, it also needs to use BGP. Now let's briefly compare the interior gateway protocols. RIP, distance vector, is a protocol. EIGRP is an advanced distance vector protocol. OSPF is a link state routing protocol. These routing protocols have metrics that they use these metrics to choose the best route. RIP version 2 uses hop count to choose the best path, meaning it looks at the nearest router information. OSPF looks at the cost values and speeds of the interfaces, and EIGRP calculates the best metric based on the bandwidth and delay information of the interfaces to choose the best way. Here's how RIP and OSPF do the metric calculation. If this router is using RIP when it goes to 10.1.1.0 subnet, it will go through the nearest router, because RIP will choose the closer route even though there is a faster connection here, since it is looking at hop count and not bandwidth speed. OSPF, on the other hand, uses bandwidth to calculate routes, so it chooses the faster route instead of the nearby router. You can also see the comparisons of IGP protocols in the table here. IPv2, EIGRP and OSPF support different subnets. You can see the algorithms they use here. They all support summarization. Only Cisco devices support EIGRP, all devices support OSPF and IPv2. All three protocols use multicast addresses for routing updates, with IPv2's converge time being slow but EIGRP and OSPF's converge time being fast. Now let's talk about administrative distances. Administrative distance is used to rate the reliability of the routing information of the neighboring router. The administrative distance is a number between 0 and 255. 0 is the most reliable, 255 is the most reliable, and if the administrative distance is 255, this is not included in the route routing table. If a router receives two updates listing the same network, the first thing the router checks is the administrative distance, which is added to the route table with the lower administrative distance. You can also see the administrative distance default values in the table here. Previously, there were RIPv2 and EIGRP subjects within the scope of CCNA training, but they have been removed from the new training curriculum. You are not responsible for them in the CCNA exam, you are only responsible for OSPF and static route subjects. The subject of EIGRP is now included in the curriculum of CCNP Enterprise Training. On this page, let me briefly tell you about OSPF terminology. Link is the network or router interface assigned to a specific network, when an interface is added to the OSPF process and is considered a link by the OSPF. Router ID is one of the many optional features of OSPF. Most enterprise companies that use OSPF prefer to configure an OSPF router ID on every router because it is important for OSPF-speaking routers to have a router ID to work properly. We have a few options for choosing a router ID. Let me tell you about them briefly. If the router ID is entered during the OSPF configuration, the router uses this ID. If no router ID is entered, if there is a loopback address configured on the router and this interface is in the upstate, the loopback interface IP with the largest IP uses the router ID. If the loopback interface is not used in the router, the IP address with the highest IP among the up interfaces is selected as the router ID. Neighbors are two or more routers with an interface in a public network, such as two routers connected by point-to-point serial link. Adjacency is the relationship between two OSPF routers that allow direct exchange of route updates. The Hello protocol provides dynamic neighbor detection and maintains neighbor relations. Hello packets are sent every 10 seconds to the multicast address 224.0.0.5. If these packets do not reach the neighboring router within 10 seconds, the router waits 40 seconds, and if it does not receive a response, it removes this route from the routing table. On this page, let's look at the terms designated router and backup designated. If there is more than one router in a subnet and OSPF neighborhoods are established, a designated router is selected among these routers. This selected router is responsible for disseminating and receiving routing information, and this selection is made to manage database exchanges. If there is more than one router in the same subnet, DR and BDR are selected between those routers. The figure below shows 5 examples of routers using the same subnet. DR and BDR will be selected between these routers, and the remaining routers will be selected as DR other routers. Now let's look at calculating the best way in OSPF. On the left side of the figure on the right, there is router 7, in the middle of which is router 1, router 5, router 6, and router 8, and on the right side is router 2, router 3, and router 4. The interfaces of each router here have different cost values. The cost value on the left side of router 1 is 10, that of router 7 is 180, on the left side of router 8 is 10, the total host value of the left side is 200. When selecting one of these three routes, OSPF will choose the one with the lowest cost value among these routes. Although the route on the left side is the shortest route, OSPF will choose the route in the middle here because it has the lowest cost value. On this page, let's talk about OSPF areas and OSPF LSA packages. In some networks that are not very thought out and not very large when designing, a single area can be used. You turn on OSPF on all routers and you put all the interfaces in the same area and it works. Larger OSPF networks can also have a single area design. For example, imagine a corporate network with 900 routers and several thousand subnets instead of 11. In such a topology, the CPU would be very hard pressed to run the SPF algorithm and it would take time to stretch. As a result, OSPF convergence time can be too slow to react to changes in the network, and routers may also have insufficient RAM. We can list the following problems related to a single area design. A larger topology also requires more memory for the router database. The larger the database, the longer the SPF algorithm process on the router takes longer and requires more CPU power. Even if there is a change in the state of an interface anywhere on the network, it will cause the SPF algorithm to work again. Now let me tell you about the OSPF areas. When designing an OSPF area, we should pay attention to a few basic rules. To enforce the rules, after the networks are properly drawn and the router interfaces are determined, we need to select the appropriate area for each router and interface, and when choosing these areas, we need to pay attention to the following. We should place all the interfaces connected to the same subnet in the same area. We should design the areas as contiguous. Some routers may have all the interfaces in a single area, but some routers may be in different areas. We call routers running in different areas at the same time as area border routers. Some of the interfaces of this router connect to the backbone area and some to the backbone area. All non-backbone areas must have a way to reach area 0 by connecting to at least one ABR router in both the backbone area and the non-backbone area. In the figure here you can see a design with 3 areas. Area 0 on the gray side has backbone router, D1 and D2 routers, where D1 and D2 routers are area border routers. The interfaces of these routers in the gray area are in area 0. D1 router has 4 interfaces in the yellow area and are in area 1. The D2 routers for remaining interfaces in the blue area are in area 2. We do the multi-area design as in this example topology. When there is a root update in area 1, it is done only with the router in this area, then the router that is ABR sends these updates to the backbone router, and the backbone router publishes this update to other ABR routers. Now let's talk briefly about OSPF LSAs. Link State Advertisement, or LSA for short. OSPF is an OSPF data packet that contains link state and routing information shared between routers. An OSPF router will only exchange LSA packets with routers that adjacency has installed. You can see information about LSA when we look at it with the show IP OSPF database command. In the table on the right you can see what LSA Type 1, Type 2, and Type 3 are used for. LSA Type 1 packet contains information such as router ID, interface, IP address, subnet mask, and status of interfaces. LSA Type 2 packet transmits information such as DR, BDR, and subnet ID. LSA Type 3 packet contains subnet ID, transmits router ID and ABR information. That's all we have to say in this lesson, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will talk theoretically about the applications in the labs that we will do with OSPF, and then we will do all of the applications I have described here together. First of all, I will explain the single area OSPF applications, the wildcard masks we use in OSPF, then there are commands we use to verify OSPF, I will talk about them, OSPF router ID configuration, multi-area OSPF configuration under interface and OSPF additional features. I'm not dwelling too much on the fact that we're going to do the practice here when we start labs, so let me tell you about the wildcards here. When we write the command line in OSPF, we use wildcard instead of subnet mask. Let's take a look at what this wildcard is, what it does. We write the networks that we will broadcast on the router with the network command. This router has a 10.0.0.0 network. The subnet mask of this network of ours is 255.0.0.0. For example, our network address is 10.0.0.0. and our subnet mask is 255.0.0.0. In OSPF, we use wildcard mask instead of subnet mask when typing the network address. How do we calculate wildcard masks? If you type 4 zeros into the wildcard, all the OSPF has to match the numbers, so if we write 0000 in the wildcard part, it will try to match them by comparing these 4 octets. If we write 10.0.0.0 in this line and 0.0.0.255 as wildcard, it will only compare the first 3 octets and the last octet will not look for a match. If we make the wildcard 20.2.255, it will only compare our first 2 octets. If we make our wildcard 0.255.255.255, it will only compare the first octet. Now there's a short method of calculating the wildcard and I'll show you that. As an example, we have 192.168.100 network. Subnet mask is 255.255.255.0. To find the wildcard of this, we write 4255 on the subnet mask. And we're taking that out of subnet mask. This is 0. This is 0. This is also 0. Here we write 255. This network's wildcard is 0.0.0.255. Let's do another example, which is 10.0.0.0. The default subnet mask of this is 255.0.0.0.0. On it we write 255, 255.255.255.255. Now we take them out and find our wildcard. We found it to be 0.255.255.255. Now let me show you how to use a different subnet mask. As an example, let's make 10.1.0.0 subnet, and the prefix of this is 30. When the prefix is 30, our subnet mask becomes 255, 255, 255, 252, where we have 30 bits. This is 24 bits, all make 255, let's write the rest here. 128, 64, 32, 16, 8, 4, 2, 1. Here we make 1, 2, 3, 4, 5, 6 bits 24 bits are here, 6 bits are here and there are 6 bits here making a total of 30. When we add them up it makes 252, what is left is 2 over 2 minus 2 for the host, which makes 2. Here, again, to find the wildcard, we write 4255 on the subnet mask and remove them from the subnet mask. When we subtract that, 0003, we write the wildcard of this network as 0003. When we use the network command in OSPF, we need to write it here as wildcard instead of subnet mask. You can calculate the wildcard in this way. On this page, let's take a look at the commands we use to validate OSPF. Show running config, show IP protocols. We will use all of these commands. You can look at this document. Here I wrote about how you can configure the OSPF router ID, which we will do together in the lab. Here we have the multi-area lab configuration. We will do this together. Here I wrote the commands we use to enable OSPF under interfaces. We can configure OSPF in two different ways. In the first method we specify our networks under the router OSPF command, and in the second method we do it under interfaces. I will show these when making labs. In our latest lab, I will show you the additional features of OSPF and talk about additional features such as passive interface, default route, metrics, load balancing. Here too is the OSPF cost calculation, where it shows the default cost values of the interfaces. The cost of a 10 megabit interface is 10, the cost value of an interface of 100 megabits, 1 gigabyte, 10 gigabytes is 1, these are the default values. You can change them if you want. We go under interface to change the cost and change it here. For example, when we make IP OSPF cost 4, the cost value of this interface becomes 4. What were the costs for? OSPF also uses these cost values when selecting route. As you can see here, the cost values have changed. That's all we have to say in this lesson. I briefly talked about the practices we will do in the lab. You will understand better when we do the labs. Goodbye, to see you in our next lesson. Hello everyone, in this lesson I will talk about OSPF network types and OSPF neighbors. First I will talk about OSPF broadcast network type, then DR and BDR manual selection, then I will talk about OSPF's point-to-point network type, and finally I will talk about OSPF's relations with its neighbors. Let's start by looking at the types of OSPF networks. OSPF uses the broadcast network type in all of its interfaces by default. Let's take an example here to better understand the OSPF broadcast network type. OSPF sends a broadcast to the 224.0.0.5 IP of all routers so that it can detect neighbors, which is an IP address reserved for routers using OSPF. Each subnet also tries to select a designated router and backup designated router. Gigabit 0/1 is DR because there is no other router, so since there is no other router here, this is a designated router on the port side, but since there are 4 routers in the subnet here, one will be selected as DR, one is BDR and the rest will be selected as DR other, DR. BDR and DR other send a broadcast packet to 224.0.0.6 or to make selection. Here we show how to determine the router ID under router OSPF1. We determine our router ID using the router ID command. Here, we can see the routers that router 1 has established with the command show IP OSPF neighbor. You can see that router 2 here is drive other, router 3 here is backup designated router, and router 4 here is designated router. Because the router ID of the router here is the largest of all, the router with the largest IP becomes the designated router, and the router with the next big IP becomes the backup designated router. Other routers become DR other routers. Here I wrote about how you can check the broadcast network type. We use the broadcast network type and default in our interfaces. You can check this with the show IP OSPF interface brief command. When you type this it shows the network type under that interface. This command does not work in Packet Tracer, but you can see the network type with the show IP OSPF interface gigabit 0 command. Let's talk a little bit about the manual selection of designated router and backup designated router on this page. If there is no designated router ID or router ID, the largest IP of the loopback interface is the largest IP of the loopback interface. If there is no loopback interface, the router ID makes the largest IP of the physical interfaces, and according to this router ID, DR and BDR are selected, but under interface we can change the priority of that interface to make that router DR. Let's take a look at the type of OSPF point-to-point network on this page. Normally, our interfaces also use the broadcast network type as the network type, but the HDLC and point-to-point protocols do not support broadcast. Because they do not support broadcast, when we use HDLC and point-to-point protocols in leaseline connections, we need to use the IP OSPF network point-to-point command under the interface. We just need to change the network type in serial interfaces. You can see it again with the SHIP OSPF interface command. Packet Tracer also does not support the brief command, but you can see it in Packet Tracer by typing SHIP OSPF interface GI0/0. On this page, let me tell you a little about OSPF neighborhood building relationships. When you enable the OSPF process in the interface of a router, OSPF tries to detect OSPF queues by sending hello messages and listening to incoming messages, but each time two routers may not be neighbors, hello packets, and various other settings that go back and forth between the two routers should have the same values. When we look at the list here, the hello and dead times should be the same on both routers. To check this, you can check the duration of the hello packets under interface using the show IP OSPF interface command. Those interfaces must be in the same area. The ID of the routers must be different. If you have used the authentication method in the OSPF process, the passwords on the two routers must be the same. The OSPF process must also be open. If one of the conditions here is not met, the OSPF neighborhood will not be established, so the values here must be the same as the neighbor. The router ID must be different and the duration of the hello packets must be the same. You can also see them by checking them with the commands here. That's all we'll tell you in this lesson for now. You'll see it in detail when we already do it in labs, so goodbye to see you in our next lesson. Hello everyone, we will make the single area OSPF configuration together with you in this lesson. Let's take a look at our network diagram. We have three routers in our topology, router 1, router 2 and router 3. All our routers will be in area 0. Router 1 has 192.168.100 subnets. Here I created the loopback 0 interface and gave the IP 192.168.101. I created this virtual interface to share a subnet between routers. In the same way here we have a loopback interface that uses the 192.168.300 subnet. Here we have the 192.168.200 subnet. Between router 1 and router 2 we use the subnet 10.1.12.0. Between router 1 and router 3 we use the subnet 10.1.13.0. We can see this in the route table because 192.168.100 subnets are directly connected on this router. 10.1.12.0 subnets are also in the route table. Likewise 10.1.1.0 network is in the route table because it is directly connected. But router 1 does not know the 192.168.20.0 and 192.168.300 subnets. We will now share unknown subnets between these routers using the OSPF routing protocol. When we share this information, router 1 will update the routing table because it learns the subnets on router 2 and add the information it receives from router 2 to the routing table, and in the same way, it will update the routing table by adding the route information it receives from router 3 to the route table. Let's do it starting from router 1. When we configure OSPF, we use the router OSPF command. Now let's put a question mark. Here we need to give a process ID number. The process ID we will give here does not need to be the same as each router, can also be different. I gave it as 1. Now we need to specify the subnets we want to share with router 1 and router 3 on this router. If there is a subnet you do not want to share, you do not need to write it. You just write the information of the subnets you want to share here. We will share the subnets on our router to neighboring routers using the network command. Here we have 192.168.100 subnet. Here we need to write wildcard instead of subnet mask. I told you how to calculate wildcard before, now let me show you again. Our subnet mask is 255.255.255.0. We write 4255 on it and we take them out. 0000255. We found the wildcard of this network, so let's write it down right away. Now we need to specify which area it is in. This subnet of ours will be in area 0. Let's write our other subnets. I come from the old command with the arrow key of my computer, it is easier to edit. I immediately write about the other subnets, 10.1.12.0. These will also be in area 0. Now let me show you one more command. This command is the do command. This command allows us to use the commands that we can use in enable mode in global config mode. For example, if you type show run here, this command will not work here, but if you type do at the beginning, then this command will work here. I checked the settings by typing do show run. We have written here the three subnet information we want to share under router OSPF. Now let's do router 2 and router 3 as well. Router OSPF, I write 1, you can write 2 here if you want. Let's write the networks we will share. 192.168.2.0.0, let's write a wildcard. We write down which area it is. Let's write our other network. 10.1.12.0. Here we are also done. Now let's go to router 3. You can see here that our neighborhood has been established with router 1. Now let's do the router 3 and then we will check our settings. I'm making the same settings here. Here we have 192.168.3.0.0 subnet. Let's write our wildcard. Area 0. I misspelled the network part. We can make such mistakes because I did not complete it with the tab key. After fixing this, let's write down our other network. I'm changing this place to 10.1.13.0. Let's end by saying end. Now let's check it by going to router 1. It shows here that the neighborhood has been established on router 1. With the show IP OSPF neighbor command, we can see the information of the routers we have established a neighborhood here. It shows that we have 2 neighbors here. The router ID of this neighbor is 192.168.2.0.1 and this is 30.1. This is where 20.1 is it. Since we did not configure the router ID on these routers, he chose the largest IP of the loopback interface on the router as the router ID, and if there was no loopback interface on our router, he would choose the largest IP among the physical interfaces and make the router ID. Here it shows that there is a backup designated router on the 2 neighboring routers, but normally these routers have to be designated routers, because the IPs of the routers here are greater than the router 1. But because we did our configuration on router 1 first, and in the other routers there was no configuration at that time, router 1 shows itself as a designated router, because there were no other OSPF routers on the network, so it declared itself as Doctor when we restart the OSPF process. This router BDR will be DR on the other routers. Now let's go to router 2 and router 3 and get the OSPF process working again. Close and open the interface here and the OSPF process will run automatically. Interface gigabit 0/0. I'm doing shutdown. Our connection is gone now. I open it again by typing no shutdown. Now I'm doing the same with router 3. Now we have 3 OSPF powered routers in our network. Router 1 and router 3 are actually being chosen right now. Router 1 and router 2 are also being chosen. This router has to win the election because its IP is bigger than the IP of router 1. Between these 2 routers, this router needs to win. This is DR. Router 1 needs to have BDR. Let's look at it with the show IP OSPF neighbor command. At the moment, the connection has also been made with router 2. Let's look again. At the moment with router 3, DR and BDR selection is in progress. In a moment, the connection of this place will be completed. Now the connection to this place is completed. When we look at it from router 1, we see that router 2 is drive, in the same way that when we look at router 1, we see that router 3 is drive. Now let's look at router 2. Here we can now use the do command do show run I write. In the same way you can use it in other commands, do ship OSPF neighbor, I wrote them briefly. When we look at it from router 2, router 1 sees its neighbor as BDR. Now let's go to router 1 and check the route table. When we type show IP route, it shows all the routes here. The letter O here indicates the routes learned from OSPF. He learned 20.0 and 30.0 subnets from OSPF, because he did not only know these two subnets. Router 2 shared route with router 1, in the same way router 3 updated the route table by sharing route with router 1. If you type show IP route OSPF, the routing table shows only routes learned from OSPF. Here we see that he learned his 20.0 and 30.0 subnet through OSPF. Now let's look at router 2. When we type show IP route OSPF, it shows us the routes learned with OSPF. This router did not know 10.1.13.0 subnet, he learned through OSPF through router 1. He also learned the 192.168.100 subnet from router 1. He didn't know his 30.0 subnet either, so he learned it from router 1. Now let's go to router 3. Let's write show IP route OSPF. Router 3 has not learned the 20.0 subnet from router 1, so let's get the OSPF process running again on router 2. On router 2, I switch to interface and turn it off and on again. Now it is negotiating with router 1 again. First the DR and BDR selections will be made, then the database will be shared between the routers and the routing tables will be updated. Let me speed up the process here. Now that we have a connection with router 1, when I type show IP route OSPF, we see the 30.0 subnet here. Having learned the 10.0 and 10.1.13.0 subnets, let's look at router 3 again. He just learned about his 10.0 subnet and his 10.1.12.0 subnet, but he didn't learn his 20.0 subnet, so let's look again. When we look again, we see that he has now learned the 20.0 subnet. That's all in our single area OSPF configuration. We had previously manually typed our subnets in IP version 4 static route to go to neighboring routers, but now in OSPF, we have shared the subnet information to the neighboring routers by making an OSPF connection to our neighboring routers using the dynamic routing protocol. The neighboring routers have also shared the subnet information on them, and now our users here have gone to the subnets here. Now they can go through the router here, so see you in our next lesson. Hello everyone, in this lesson we will use the same lab that we did before, but differently we will configure OSPF under interfaces. In our previous application, we shared our network information under the router OSPF command line. Here we will do it under interfaces instead of under the router OSPF command. Now let's start our configuration. Let's start with router 1. First we activate OSPF with our router OSPF command. Let's write a router ID here, and the ID of this router is 1111. I log out by typing exit. You don't have to type in the router ID, this feature is optional. If you don't type it, the largest IP of the loopback interface or physical interface is selected as the router ID. We have 1, 2, 3 interfaces here. Let's go under these interfaces. Interface loopback 0. Our command here is IP OSPF1, where 1 is the OSPF process number. After writing the process number, we write which area this interface is in. Let's move on to our other interface. I write interface gigabit 0/0. Our command is again the same IP OSPF1 area 0. Now let's do gigabit 0/1. Now let's check our configuration by typing show run. As you can see here, we indicate that we will use IP OSPF process 1 under the interfaces and that this interface is in area 0. When a neighbor is established between this router and this router, OSPF will share the subnet information on this network with this router. Now let's do router 2. Here I also make the OSPF process number 2. As I said, you can do it differently on each router. Let's write a router ID in this, and its router ID is 22. In this router we have two interfaces. Interface loopback 0, where our process ID is 2, our process ID may be different, but our area must be the same. If you make the areas different in these interfaces, the neighborhood will not be established. Now I also do interface gigabit 0/0, in which I write IP OSPF 2 area 0 in the same way. Now let's do the router 3 as well. Let the process ID of this place be 3. Let 33 be in our router ID. Now let's do the interfaces. Interface loopback 0, IP OSPF 3 area 0. Let's also do interface gigabit 0 watt. Here I write IP OSPF 3 area 0 in the same way. Now let's go to router 1 and do our check. We are now on router 1. Here you can see that the neighborhood has been established with router 2. The 2 that we have determined when establishing a neighborhood with router 2 uses the 2 router ID. Now we have a connection with router 3. Let's look at it with the command show IP OSPF neighbor. First we have configured this router. This router has chosen itself as a designated router. Since we have configured the other routers later, these routers have become BDR. Now when we restart the OSPF processes, the selection will start again and these routers will be DR because the router IDs of these routers are larger. Let's turn the 2 interfaces here off and on. Interface gigabit 0/0. I'm doing shutdown. I turn it back on, I do no shutdown. Let's do gigabit 0 to 1 as well. Let me show you another feature that I haven't shown before. There is a real-time and simulation mode here. We are in real-time mode right now. When we switch to simulation mode, we can see the hello packages that take place here. Now I click on the simulation. There are all the options in the list right now. I delete it by saying none. I say edit filter again and I want it to show OSPF related packages in IP version 4. When I press play here, we can now see the traffic going back and forth between the routers here. Right now router 3 has sent router to 1. Now switch to router 2. No neighbors have yet been established. You can watch it this way from here. It is currently sending from router 2 to router 1. Again it went from router 1 to router 2. Hello packages here go back and forth between neighbors every 10 seconds, and from here we can see the packages. Let's switch back to real-time mode. Here you have seen the simulation mode, where you can test the feature you want. Now let's open router 1 in real time. Let's look at the neighborhood situation with the show IP OSPF neighbor command. When we look at it from router 1, the router ID of router 2 is 22. Router 3's router ID 33. As you can see, router 2 and router 3 are now drive, because their IDs are larger, so they are DR and router 1 is BDR. Now let's look at the routes we learned with the show IP route OSPF command. When we look at it from router 1, we don't just know the subnet here and the subnet here. But we know this because this subnet is directly connected. We know this because this subnet is directly connected. We know this, but we do not know this subnet with this subnet. We have learned these subnets through OSPF. Now let's go to router 2. When we look at it from router 2 knows 20.0 and 12.0, not 10.0, 13.0, and 30.0. Let's write show IP route OSPF. Here he shows the routes he learned from router 1 via gigabit 0/0 interface. 13.0 subnet, 192.168.100 and 30.0 subnets. Now let's look at router 3. I am writing show IP route OSPF. Router 3 has not learned the 20.0 subnet. Let's restart our OSPF process here. Let's turn our interface here close and open. Now let's wait for the establishment of the neighborhood. Now that we have a neighborly connection with router 1, let's check our routing table again. Let's wait a little while. If we still haven't found out, then let's look again. Now he has learned the 20.0 subnet. When I ran the OSPF process again, the route information was updated. We did this process so as not to wait. The route tables would be updated with the next OSPF LSA packages, but I closed and opened the interfaces to restart the OSPF process so that the operations would be fast. This is how we configure OSPF under interface. Configuring OSPF under interface is easier than the first method we did because we do not enter network information one by one under the router OSPF command line. we directly add the information of that interface to the routing table with the IP OSPF command under the interface. Goodbye, to see you in our next lesson. Hello everyone, I will show you the IPv4 floating static route configuration in this lesson. I said earlier that when I was dealing with the IP version 4 static route topic, I would tell you about it when we were dealing with OSPF, because then we had not yet covered OSPF and you didn't know about OSPF. But now that we have done labs on OSPF and now that you have learned about OSPF, we can now do the floating route configuration. Now let's look at our scenario here. Our users on the router 1 side access the server in the data center. In order to access the server, there is an OSPF configuration between router 1 and router 2. Router 1 has a second backup connection to the data center via the lease line. When our OSPF connection is broken, our hosts here need to access the server here using this line as a backup. In the current scenario, all IPs are configured, and OSPF is currently running between router 1 and router 2. So our hosts here can go to server 2, but when our OSPF connection is broken, our users here have access to the server, so we will write static route on router 1 and make it go to the server here via router 3 when the OSPF connection goes. Let's first test and see if it goes or not. Let's open router 1. The IP of our computer is 2.3. I write ping 192.168.23. First there will be some timeout because there is no traffic between them before. An ARP packet will go back and forth between them first, then our packet will be forwarded. As you can see, our ping was successful. Let's check which way we are going by doing traceroute. Let's use the traceroute command to see which way we used to go to 192.168.23. Our router here comes to 10.1.12.2, from where it accesses the server. When our OSPF connection here goes, we need to write a static route here for our traffic to go from here. Let's write show IP route. Here we learned the 192.168.2.0 subnet with OSPF, and we will make the administrative distance 110 and the administrative distance of the static route we will write to 130, that is, we will give a lower level of reliability than OSPF, so our route will go through OSPF first, so it will continue to go from here. Now let's write our route. Forward the packages to 10.1.13.3 next hop to go to 192.168.20 subnet. When we put a question mark, it shows that we can write an administrative distance between 0 and 255 here. Here I write 130 as AD. When we check with show IP route, we cannot see the static route we write here, because when the router goes to the 192.168.2.0 subnet, the OSPF does not add static route to the route table because the administrative distance value is better. Only the active routes appear here. We can see the static route that we have written when we check our settings with show run. You can see the static route we wrote here, but since our OSPF connection is active now, this route is waiting as a backup. Now let's terminate our OSPF connection. I am closing the interface where we have an OSPF connection. Now that we have lost the connection between router 1 and router 2, if we did not have static route here, router 1 would have been disconnected from data center, but our traffic would not be interrupted because it is our backup connection. Now let's check our route table by typing show IP route again. Now that we have lost the OSPF connection, you can see here that static route has been added to the routing table. The administrative distance value of this route is 130. Now let's ping 192.168.22. Our ping is going to 2.2, let's do a traceroute. As you can see, it goes to 2.2, let's go to 2.1, let's see if we have access here. We don't have access here right now, because the OSPF connection here is gone, so now router 2 has no route to router 1, and when the OSPF connection goes, we need to write a static route on router 2 so that it can access router 1. Now let's add a static route on router 2. When we write show IP route, it only knows its 2.0 subnet here, and the interface on the first side of the router does not show its 12.0 subnet in the routing table because it is not currently active. Router 2 learned 192.168.10.0, 20.0, and 13.0 subnets from router 1 with OSPF, but now that the OSPF connection is gone, it does not know these networks. We need to add these networks here via static route. Let's write it right away. IP route 192.168.100. Let's write our subnet mask. Let's make the administrative distance of this 130 so that when OSPF is activated, it will add the routes it has learned from OSPF to the routing table. We did not write our next hop address. Let's write this. Let it go through 192.168.22. Now let's do it for 20.0 as well. To go to 20.0, let him come here in the same way. Now let's do 13.0 as well. Now let's log out and come to router 1. I'm currently pinging from router 1 to 2.1. We now have access to 2.1, let's do a traceroute. At the moment, our traffic to 2.1 is provided through router 3, let's try 2.3. Our ping is going to 2.3, now let's do a traceroute. Now that our traffic is flowing from here, let's open OSPF again and see what happens. On router 1 I write CONFT, interface gigabit 0/0. Now let's open our port and wait for our OSPF connection to be established. When OSPF neighborliness is established between router 1 and router 2, the route tables will be updated. After the tables are updated, let's do our tests again. At the moment our OSPF neighborhood has been established. Now when we write show IP route, the routing table has been updated because OSPF is now active. We will now go through 10.1.12.2 when going to 192.168.20 subnet. Now let's ping. When I type ping 192.168.23 we can access the server. Let's look at which path we're taking. I write traceroute 192.168.23. Now that OSPF is enabled, router 1 uses the route on router 2 to access the server in the data center. Now let's check if our static route will automatically be activated when we disable OSPF again. Here I turn off interface again. Now let's do a traceroute to 2.3 again. You can now see that router 1 uses the backup connection on router 3 to access data center. Friends, you can also configure static floating route this way. That's all we have to tell you about in this lesson. Goodbye to see you in our next lesson. Hello everyone, we will make the multi-area OSPF configuration together with you in this lesson. Let's start by looking at our lab topology. We use area 0 in the local network on the yellow side of router 1. The gigabit 0/0 and gigabit 0 to 1 interfaces of router 1 are in area 23. The blue side of router 1 is in area 4. Now we can start our configuration. When configuring OSPF, it would be more practical to do it under the interface. Let's not bother with going under the router OSPF command and writing the network command. Let our router OSPF process number be 1. I make the router ID of this place big so that it is a designated router. Now let's go under interface. First let's do interface loopback 0. Our command is IP OSPF process ID 1, our loopback interfaces here are in area 0. Likewise, I take loopback 1 to area 0. I exit and enter interface gigabit 0/0. This interface is in area 23. Let's do gigabit 0 to 1, which will also be area 23. I exit and switch to interface gigabit 0/2, which will have an OSPF process ID of 1 and an area of 4. I quit by typing end. Now I switch to router 2. Let the router OSPF, our process ID be 1, and the router ID be 2. I go under interface by exiting. Let's do interface loopback 0 first. I write IP OSPF 1 area 23. Let's make interface gigabit 0/0 the same way. Now let's go to router 3. Here I write router OSPF 1. Let the router ID be 33. I log out and switch to interfaces. Interface loopback 0. I write IP OSPF 1 area 23. I took the router 3 interfaces to area 23. Now let's move on to router 4. Here we activate OSPF by typing router OSPF 1, and here we make our router ID 44. Let's enable OSPF under interfaces by exiting. IP OSPF will be process ID 1, area will be 4. Let's do the same with interface gigabit 0/0. Now let's look at router 1. Let's look at the neighbor situations by typing show IP OSPF neighbor. We have established a connection with router 2 and router 4, and we have not yet established a connection with router 3. Let's check the settings of router 3. Here I guess we have not made the interfaces. Let's check it immediately with show run. Neighborliness was not established because we did not enable OSPF under interface gigabit 0/0. Now let's set it up here. I get out of here by typing IP OSPF 1 area 23. Now I come back to router 1, and now we have a connection to router 3. When we look at it from router 1, it sees all its neighbors as BDR, and it has become a DR itself. Let's look at it from router 2. Let's write show IP OSPF neighbor. It shows that a neighbor is established between router 2 and router 1, 55 in the neighbor's router ID. Since router 1's ID is large, it became a DR router. Now let's check the route table on router 1. Let's look at the routes we learned only from OSPF by typing show IP route OSPF. Router 1 already knows the networks that are on it, knows the 10.1.12.0, 10.1.13.0 and 10.1.14.0 subnets, but he did not know the 3 subnets here. He learned these subnets through the routers here. Let's look at it with the show IP protocols command. Here it shows that our process ID is 1, our router ID is 55, and here it shows our neighboring gateways. Now let's use the show IP OSPF interface command, where we can't look at it because packet tracer doesn't support the brief command. We can check it by typing the interface number here. When we look at gigabit 0/0, here it shows the interface address, OSPF process ID and router ID. The network type shows the cost and the status for this interface is DR, 2 shows 2 as BDR. Now let's look at router 2 as well. The letters IA here mean inter-area. It shows that it learned its 10.1.1 IP from 10.1.12.1, that is, from router 1, and since there is more than one area on router 1, this router becomes an area border router and can share to routers in other areas. Let's look at it with the show IP OSPF command. When we look at it with the show IP OSPF command, we can see the OSPF process ID, the router ID and the area border router of this router. This router is also the backbone area because its interfaces are in different areas. This is how we do the multi-area OSPF configuration. So see you in our next lesson. Goodbye. Hello everyone, in this lesson we will make the DR and BDR selections by changing the priority of the interfaces to determine the OSPF to designated routers and backup designated routers. In our topology we gave the IPs of all the interfaces and I integrated the OSPF. The ID of the router here is 11, here is 22, here is the router is 33. Since the ID of router 2 is large between router 1 and router 2, this is DR. Since the ID of this place is big between router 1 and router 3, this is DR and router 1 is BDR, but let's change the priority under interfaces so that router 1 is a designated router. Let's check our settings by turning on router 1 first. When we type show IP OSPF neighbor you can see that router 2 and router 3 are drive here, but we want router 1 to be drive. We can make it DR by changing the ID of router 1, but since I have shown you how to do this before, let me show you how we make DR and BDR selection by changing the priority of the interfaces in this lab. Interface gigabit I enter 0/0, our command is IP OSPF priority, I am making a question mark here. We can enter a value between 0 and 255. If we make the priority of this interface 0, this router will not participate in the DR and BDR selection. It will be the DR other router because it does not participate in the selection. Let's make the priority value of this 2, since the default priority value of the interface here is 1, the interface here will win the selection and there will be DR between router 1 and router 2. If you make 255, it sets itself directly as DR. On gigabit 0/1, I make its priority to 2 and turn off both of these interfaces. By opening these interfaces again, I make the OSPF process work again. Now let's take a look at it from here by opening the simulation mode. Right now, hello packages are going back and forth. I remove all the features here and make it show only OSPF packets in IPv4. Here you can see the hello packs go back and forth when I press play. You can also follow it here. The packet is now on router 3. It goes from router 3 to router 1. Now it goes from router 1 to router 2, so you can see the packets going back and forth here. Now let's go back to real-time mode and check our settings on router 1. A neighbor has not yet been established, and our neighborliness will be established in a moment. Our neighborhood with router 2 has been established, coming soon with router 3. Now that it has arrived on router 3, let's look at it with the command show IP OSPF neighbor. We can see that router 2 and router 3 are BDR. Here you can see that the priority of the neighboring routers is 1. Now let's look at router 2. I am writing show IP OSPF neighbor. Here you can see that the priority value of router 1 is 2 and it is DR. We made router 1 DR by making the priority value of interface here 2, in the same way we did it in our gigabit 0/1 interface. Now let's look at router 3. I am writing show IP OSPF neighbor. Here you can see that the priority value of router 1 is 2 and it is Dr. This is how you can make DR and BDR selections by changing the priority values under interfaces. Goodbye to see you in our next lesson. Hello everyone, in this lesson I will show you how to change the passive interface, default route sharing and cost value from the additional features of OSPF. First of all, let me talk about the passive interface. We have 3 routers in our local area network, where router 1 has a WAN connection on one side. Since OSPF is active in all 3 routers here, hello packets go back and forth from all interfaces, but since we do not have an OSPF connection with the ISP, we want to cut OSPF hello packets from this interface and prevent unnecessary traffic that will occur, so we make this interface a passive interface. As for the default route, our router here is our internet output router. There is a default route on it. We can send this default route to our other routers via OSPF. Let me show you how it is done a little later. Cost use the cost values of the interfaces to find the best route in OSPF, and I'll show you how to change those cost values in a moment. For example, there are 6 routes on this router and we have learned all of them from OSPF, but if we want, we can change the priority of these routes by changing the cost of these interfaces. First, let's do the passive interface, then let's do the default route, and finally let's finish our lesson by showing how you can change the cost value. Now let's start with router 1, our OSPF process ID here is 1. I write router OSPF 1, I write passive interface, our passive interface will be gigabit 0/2. We have made the gigabit 0/2 port passive. Now let's check our settings by exiting. OSPF hello packets will no longer be sent over this interface. Now let's look at the default route. We have one default route in this router. We will share this route information to other routers over OSPF. Since this router is also the default route, this router has access to the internet. Let's test it right away. This router has access to the internet, so let's look here. When we ping, our ping does not go away because it does not know the route. We will now send the default route from router 1 to these routers via OSPF. Let's write show IP route. This router has only learned 10.1.20 subnet from OSPF, but there is no default route information. Now let's configure it on router 1. I write router OSPF 1, our command is default information originate. Let's connect to the v1 router again. Let's write show IP route again. When we type show IP route, it shows the default route as OSPF v2. OSPF v2 means external type 2. Now let's try to access the internet again. As you can see, you can now access the internet on these routers. Let's do a traceroute. First it goes to 10.1.10.1, from there it goes to the ISP, and from the ISP it accesses 8.8. This is how we can broadcast the default route through OSPF. Now let me show you how to change the cost on router 1. Interface gigabit 0/0. Our command is IP OSPF cost. Here I change the cost value by making it 10. Now we can check by typing show IP OSPF interface gigabit 0/0. Here he gives us information about the interface. As you can see, this shows that the interface's cost value is 10. Let's look at the other interface. Since we have not changed this interface, we can see that this is default 1. Friends, this is how we can set the passive interface, default route and cost. So goodbye to see you in our next lesson.